Hi, I'm Yoav Columbus, and we'll talk about auctions between regret minimizing agents. This is a joint work with Noam Nissan. So we're going to talk about settings where several users interact over some online platform. These users are assisted by software agents that play the repeated game and optimize on their behalf. And the types of games we'll focus on are online auctions, like the ones used by the large internet companies to sell ad positions online. And an important example are the keyword auctions, like the ones we see on search results web pages, like here on the right. And the way this basically works is that every time we enter a search query for some keyword, then the platform runs an auction between the advertisers, who are the players in this auction. And each one of them places a bid, which is the maximum amount he is willing to pay for a click on his ad. And the auction then sets the allocations of ad positions and payments for the players. So this is a huge industry, and these auctions run at an enormous rate. And in fact, it's so fast that it's not really practical or not even possible to manually place a bid for each and every auction. And so most of the bids are being placed by various auto bidding tools. And the way this basically works is that users enter their key parameters into the auto bidding agent interface. And then the agents automatically place bids, interact, and learn. And the users can observe the long-term outcomes. So to illustrate this, let's say that Alice and Bob are users in some online platform. Then in the classic auction setting, each one of them places a bid in every auction. And then the auction returns the allocations and payments. And Alice and Bob have some utility, and this goes on repeatedly. When we move to the auto bidding setting, things are a bit different. Here, Alice and Bob define for their agents the maximum allowed bid, and then the agents place bids in a series of auctions, and Alice and Bob can observe the long-term outcomes from this series of auctions, and they have some utility from these outcomes. So what happens in this gray box here is in fact that every agent is running some learning algorithm that aims to optimize the utility for its user. But it optimizes according to the parameters that were reported by the user. And so, in fact, Alice and Bob are not really playing the original auction as it was defined by the platform, but instead they are playing what we call a meta auction, in which their actions are the parameters that they choose to give to their agents, and their utilities are determined by the dynamics of these agents. And I'll just mention that this metagame model is more general. You can think about it in other settings as well, and we do that in a different paper. It opens many interesting questions. So the types of learning agents we'll consider are regret minimizing agents, which means that they play such that the long-term average empirical payoffs approach the payoff of the best fixed strategy in hindsight. So they do not regret not playing this fixed strategy. There are many well-known examples for such algorithms, like multiplicative weights, follow the perturbed leader, online gradient descent, so on and so forth. Importantly, it has been shown that real-world bids in these ad auctions are by large consistent with the regret minimization model. And we know that the dynamics of regret minimizing agents approach the set of what is called coarse correlated equilibria of the game. In fact, by definition, if all agents have low regrets, then the joint action distribution is close to a coarse equilibrium. But we also know that the set of coarse equilibria may be quite large in many games, also in our auctions. Maybe too large to analyze quantities of interest here, like the player's utilities, revenue, and social welfare. So to analyze these quantities, we'll need to look deeper into the dynamics and see what's actually going on in these games. And the types of auctions we look at are second price and first price auctions and their generalized versions. The second price auction is known to be incentive compatible. And so perhaps it would be natural to expect that we'll get the second price outcome, meaning that the player with the higher value is going to win and is going to pay the second price. Now, the first price auction is not incentive compatible, but it is known that its Nash and correlated equilibria all yield the second price outcome. But it's also known that this auction has other coarse equilibria. Some of them are even not efficient. So here it's less clear what we should expect. Are we going to get the second price outcome, or are we going to get one of these other equilibria? So the questions we are going to ask are, first, what are going to be the outcomes when learning agents, specifically regret minimizing agents, play these auctions? And second, what parameters should the users report to their own agents? Specifically, is it in the best interest of a user to truthfully report his value to his own learning agent? It may seem natural because the agent is optimizing for this value, but we'll see. And as I said, to answer these questions, we'll need to dive deeper into the dynamics and to understand what is in fact the metagame that these users are playing. And we'll see that the first point here is in fact not correct. We are not going to get the second price outcome in the second price auction. Whereas the second point here is correct. We are going to get the second price outcome in the first price auction. And this is a result that we found quite surprising when we started analyzing these auctions. And of course, there's lots of related work. I won't get into it due to lack of time, but you can read more details about it in the paper. So start from the second price auction. A result says that in the limit empirical distribution of multiplicative weights agents in the second price auction with values V and W, the high agent is going to bid uniformly between the second price and its value, and the low agent is going to bid with full support between 0 and its value, which is the second price, with monotone density. And so the high agent is going to always win, but is going to pay strictly less than the second price. So we're not getting the second price outcome. And this is indeed what we see in simulations. Here we have a simulation of two players with the values of 1 and 1/2. And we see the bids over time, and the solid lines show running window averages of the bids over 100 auctions. And we see that indeed the high agent always wins, except for a small number of auctions in the beginning. And the bids of the low agent are much lower on average than the second price. So the average bid here is 0.27, which is significantly less than the second price. And this average bid is the price that the high agent is going to pay. And on the right, we see the bid densities of the two agents. And we see that indeed it behaves as the theorem says. In these simulations, the high agent bids uniformly between the second price and its value. And the low agent bids with monotone density with full support below the second price. And this result has a corollary that from the perspective of the users, we are not getting the second price outcome. So the second price auction with multiplicative weights agents is not incentive compatible. And we can see this in the following example. Let's say that Alice has a value of 0.4 and Bob has a value of 0.5. And now let's assume that Bob is going to report his true value to his own learning agent. Now, what should Alice do? So if Alice is going to use her true value of 0.4, then she's going to always lose the auction and get 0 utility on average. But if Alice is going to manipulate her own agent by misreporting her value as a higher value of 1, then she's going to always win the auction. And in fact, we're going to get exactly these dynamics that we saw. And she's going to have on average positive utility. So we see that truthful declarations are definitely not a dominant strategy. And in fact, they're not even an equilibrium. So the users do have incentives to manipulate their own learning agents to misreport their values. And we're not getting incentive compatibility in the second price auction. Now, when we move to the first price auction, we have this result that says that in the first price auction, between any two mean-based regret minimizing agents, and mean-based learning algorithms are a family of algorithms defined by Braverman et al. That includes many algorithms like multiplicative weights and many others. And so if the dynamics converge to any single distribution, then the high player, the high agent is going to always win and is going to pay the second price. So we are getting the second price outcome. And indeed, we see this in simulations. So on the left, we have a simulation like the one that we saw before with two agents, one with a value of 1, the other one with a value of 1/2. And we see the bids over time. we see that indeed the high agent always wins, except for a small number of auctions in the beginning. And his bids converge to the second price of 1/2. And the bids of the other agents are somewhere below that. And on the right, we see a different simulation with symmetric agents, both with a value of 1. And we see that the bids converge to the second price of 1 in this case, but convergence is very slow. And in the inset, we see a simulation of 1,000,000 auctions in a logarithmic scale for the time, for the horizontal axis. And we see that the convergence is very slow, but still the bids converge to the second price. And this result has an interesting corollary that from the perspective of the users, they see a second price auction when they report their values to their agents. And so the first price auction with mean-based regret minimizing agents is incentive compatible. And this is in contrast to what we saw in the second price auction. So the idea of the proof at the very high level is that first we define a refinement of the class of coarse equilibria that we call Cohen-dominated. And in these equilibria, players do not play actions that are weakly dominated by any of their other actions, but only relative to the support of the actions of the opponent. Then we have a lemma that says that in any finite game, if the dynamics of mean-based agents converge to a single coarse equilibrium, then it must be Cohen-dominated. So this is in any game, not only auctions. Then we have another lemma that connects this back to our auction and shows that in the first price auction, in any Cohen-dominated coarse equilibrium, the high player is going to always win and is going to pay the second price. So this is the overall structure. And we also study generalized first price auctions. So I'll just mention the results briefly here. So first we calculate the unique mixed Nash equilibrium for this auction, which apparently wasn't known. And then we see that the agents do not converge to this equilibrium, to this Nash equilibrium, and we characterize the empirical equilibrium that is obtained by multiplicative weights agents. So this is empirical analysis, not proofs. And then we analyze the equilibria of the metagame between the users who report their parameters to their agents for the case of symmetric users. We see that in this equilibria, one of the users is going to report a very high value, arbitrarily high value to his own agent, and the other user is going to use a very low value, 0.54 of his true value. And in fact, the users are locked in a kind of a hawk-dove game between themselves, where every player prefers to be the high bidder, but if both use high values for their agents, then both are going to lose. And interestingly, these strategic manipulations lead in these equilibria, lead to significant collusion. So the users capture 89% of the welfare, which leaves only a small fraction to the auctioneer, which is probably against the interests of the auctioneer or of the platform designer. So to recap, our conclusions are that first, we see that the dynamics of learning agents induce a metagame on the users. And these metagames sometimes may have significant differences, significantly different properties than the original game was defined. And we study other metagames in other settings in a companion paper. And second, perhaps a takeaway message is that our results show the types of phenomena that can happen in the auto bidding world. And things can be quite different. And we saw that second price auctions in the auto bidding setting may lose their incentive compatibility. And we saw this for multiplicative weights. We saw that first price auctions become incentive compatible, at least for a large class of regret minimizing agents. And there are lots of interesting questions for future work, studying more metagames, studying dynamics in other, perhaps more complex auctions, and maybe designing agents that do something better than just minimize regret. Thank you.